Alrighty, so this is gonna be the first video on my channel. So I just made this channel for like funsies. I have nothing else to do. So we're gonna be going over one of my review exams from Physics 4A, review exam 1. We're not gonna do all the problems, obviously. I'm gonna make this a short video. We'll try to solve this Canon problem here, this thingy right here. Yeah, so let's get started. Let's make this short. It's not take too long. As you can see, I'm doing it on my iPad, so that makes it convenient. So obviously the answer is already given right here, so that makes it even more convenient. So that way we know our answer is correct once we get our answer. So it's asking that, so it's basically telling us a cannon fires a projectile with a initial speed of 800 feet per second to hit a target located 300 feet away. So whenever we're reading a physics problem, we always write down what's known. So let's continue on what it's saying. The projectile must be aimed at a specific spot above the target. So obviously it's going to be like aimed like somewhere above the target right here. It says calculate the height in feet above the target where the cannon should be aimed to ensure the projectile hits its mark. So let's write down first what it's now. Let's first write down some more initial information, just what can be taken away from this problem based off the information that's already given. So we know that the initial velocity, well, it gives us the magnitude, doesn't give us like x or y direction. It doesn't give us the components. So we know the magnitude of the velocity or the speed, whatever you guys want to say, is 800 or 8 times 10 to the squared feet per second. And the target, or basically where we want the projectile to land, is located, which is obviously in the x direction. So it's located 3 times 10 to the squared, 3 times 10 to the 2 feet per second. So that's the only information that's given, and it also gives us g. So we know that g in this case, everything's in feet, so it conveniently gives us g in feet per second squared. So this is the g we'll be using in our calculation. Now, whenever solving a physics problem, it's very convenient to draw out our situation. That way we'll have like a good visual idea of what the hell is actually going on. So let's draw our coordinate plane, x, y, because everything in physics usually is on a coordinate plane when we're dealing with vectors. So over here is our cannon. So it says we will draw our velocity vector, bam. So that's the magnitude of our velocity. And we obviously know it's going to be at some angle, theta. And if we were to draw like actually let's fix up something a little bit. It's just something I want to do. Let's extend this a little bit. That way we have more space. Okay, so assuming that, let's say this spot right here is x of f, which is where the projectile, or not the projectile, where the target is located. So assuming the trajectory or the line of motion goes like this, that looks really bad. Some upside down parabolic shape, curved shape down. So assuming it goes down like this, obviously due to gravity. So we need to find what essentially the height at which this cannon right here needs to be pointed above the target. So basically what we're saying is that there's like this massive triangle. So essentially we need to find this height right here, which is like just one massive triangle with like this angle right here. So it would be convenient to find this angle. But before we dive into that and make early conclusions, we need to figure out what equations we need to use. So obviously we'll be using the kinematic equations. So we know that the first one, or like the first there's usually 4 general kinematic equations. I think the most helpful one, well, we'll just write down just like the first 2, because I don't think we need the other 2 to solve this problem. So there's this one. Well, x, this doesn't really matter in this case, because you can either put x depending on which direction you're talking about, because this can be just changed to y if we're talking about like the y direction. I just put x for like as a placeholder. It doesn't really matter. And then suppose we're talking about, and this is the second kinematic equation. It's just again, we only have the x there. You can change it to y, doesn't matter. This just means like it's in the x direction. We're talking about motion in the x direction. So this is the second kinematic equation, 1/2 at squared. So we know that the velocity is, we're given the magnitude, and we know that also to find theta, we know theta is equal to the inverse tangent of y over x, or tan theta is equal to y over x from trig. And we also know that the magnitude of the velocity, which is I don't want to rewrite everything actually. Well, I'll just write this. So let's go back here, right? We know that the velocity vector can actually be broken into 2 components. There's the, use a different color marker. So this could be actually broken into 2 components. There's the x component, there's the y component. So the y component is just the magnitude of the velocity vector, sine theta, and the value or the x component of the velocity vector is just the magnitude cosine theta. Now all we have to do is, obviously, I just like to write down everything we know. So we know the velocity in the x direction is just the cosine. And then the y direction, same thing, just sine theta. Obviously just using trig. Once we have that, now we can start using our kinematic equations. So I'd say the first one, I guess we don't really need to use this one, although you could if you want to, but I think it'll be more useful to use this one to solve our specific problem. So if we go about solving for x, right, using it for the x direction, so suppose we're working with the x-axis, motion in the x direction. So for x direction motion, we will use, so our final, we know that our final point where the where it's gonna land is already given, which is 300 feet. So I'll just put x, or I'll just put 300 feet. Is equal to x naught. X naught is obviously 0, so we don't really need that. Or we can just write down everything. 0. We know our initial velocity. Actually, these are technically initial velocities. Our initial velocity in the x direction is the magnitude of v cosine theta. Just so you know, theta is not known. Plus, well, there's no acceleration in the x direction. So since there's no acceleration in the x direction, this term cancels out as well. Now, for the y motion, we know that our final point when it lands is going to be at 0 feet, because obviously when it lands it goes here, eventually reaching its like maximum height, and then obviously it dips back down to the ground, which is 0 feet. And we know that our initial height is also 0, so we can just say this term cancels out. We know that our initial velocity in the y direction is given too, so which is whatever we found here. Here's just the magnitude of the velocity sine theta. Don't forget the t1. So this is 1/2. Remember to use the correct value for g, which is right here, which is gravity. So gravity is acting in the negative direction. We put negative 32.2 feet per second, t squared. So that's our equation for the y motion. Now we want to solve for theta, obviously, so we need to find a variable that we can utilize to sort of bring these equations together. So I see that it'll be easier to do that if we we can actually simplify this equation right here. If we bring this term over here, and then we can cancel out some stuff. So since it's already a negative, that's going to help a lot. So we can bring this to the other side. So let's hold up. I think okay. Since this is already a negative right here, we can bring it to the other side. 1/2 32.2 feet per second. T squared, we're bringing this term to the other side, just so nobody gets lost. It's equal to the magnitude of v sine theta t. Well, we know that the t terms cancel out, and we're just left with just one t on this side. So that's good enough. Now we can just solve for t. So we know t is equal to, we can just move stuff to the other side, sine theta, and then we can just multiply this by 2. Obviously this, let me use a different color. 2 is cancels out 2, and then we're just dividing it by the gravity value. And so let's change it up. 32.2 feet per second squared. About the squared. Okay, so now we're here. We found out our t, and we solved for t essentially. And now we can plug this back into our x motion equation, which should be simple. So let's do that right here. Yeah. Bring this here. So we know that, just rewriting it, I'm just rewriting the motion equation for the x direction. So it's at 300 feet is the final position of our target, and obviously that term was 0. And our motion initial velocity is the magnitude of v cosine theta, and then t, which we found right here, this value is going to be plugged into that t value right there, which we're going to do down here. So we know that our value for t is just the magnitude of v sine theta times 2 divided by 32.2 feet per second squared, or g. And we do not have anything for the gravity there, so we're good on that. We don't need anything there. And now we can proceed to solve for theta. So I know we can what's it called? Okay, so yeah, obviously we have two of the magnitude velocity terms, so we can just start manipulating the equation. So I'll just rewrite everything down here, make it easier. So just moving stuff around using basic algebra, we can divide the two. Well, technically we can combine these and then say this is the magnitude of v squared. So we're gonna put that down here. We have that down here, we're dividing, and we're also gonna bring down the 2, and we're gonna bring up the gravity, feet per second squared. And now we're just left with cosine theta, sine theta. Now this is the part where you have to know what trig identity. Well, we know that, I mean, this is something you gotta search up, or if you don't remember, you gotta search it up, or maybe go back into your textbook or whatever. So we know the trig identity for cosine theta, sine theta is the same thing as sine theta. Well, no, not sine theta. Sine 2 theta over 2. Well, usually it looks like something. And you might find it like this, but then you just divide it out. And yeah, we just replace this thingy with this. So I'm just going to erase this for the time being. It's going to make it a lot easier. So let's replace it. Divided by 2. Well, these two terms cancel out because they're both on the same side. And then you can, obviously do inverse sine, so you can isolate the 2 theta, which we will do right here. Okay, and then the gravity term, can't forget that. Got that there. And let's see, what else do we need? I think that's good enough. I guess we don't really need. Let's clean it up a little bit. Looks like shit. Never mind. Okay. And then we only see the magnitude of v squared term on the bottom. And then obviously we do inverse sine. And then we're just left with 2 theta. Well, just divide out the 2, which we can just put down here. Boom, boom, gone. Now we have basically solved for our angle. Well, if we actually calculate it using our calculator. Well, I'm gonna replace this actually, because this is technically an actual value, which is located. Where is it? Right here, which is 800, or 8 times 10 to the power of 2 feet per second. And this is whole squared. Now we can actually use a calculator to figure out what that value is. Well, good for me, I actually have a built-in calculator on this, which I downloaded. Highly recommend using this app if you want to. Now, if we actually calculate it, make sure to put your calculator in degrees, which mine already happens to be in. So, luckily for me, I also have the fraction button. Sine inverse, let's put another fraction. Well, for simplicity, I'm just going to write 300. 32.2. 32.2. Bam. And then let's go to the denominator. Well, this is going to be 800 squared. And the whole thing divided by 2. And we're given that angle. Well, we found our angle theta, which is 0.4324 degrees. That's relatively low, actually. Whatever. Seems good enough. Now, since we found our angle, we can use that angle to figure out what our height is. Well, just using this knowledge right here, we can sort of change up some of the values. So in this case, in the case of our problem, we know theta, well actually this can also be written as tan theta is equal to y over x. And in this case, we know just by looking at that massive triangle we've created, this thing right here, and it's asking us to calculate the height in feet above the target, which is this height. Imagine if we just drawing a line. Well, we know our x value in this case is just the distance to the target, xf, and our y in this case is just going to be the height at which the cannon is pointed at. So if we were to draw a line, so y in this case is h, just by looking at it. This is y, and this is x, and then x in this case is just the final distance to where the target is. Now we can just, I don't know, manipulate that equation a little bit. Move x to the other side, and then put h here, and then solve for h, which we already did. Well, you know, this x, basically the distance to the projectile is just 3 times 10 to the power of 2 feet. And then theta is just this value. I'm not gonna write it, so we'll find our h, which is technically equal to, using our calculator, I'm gonna again write 300, and theta tan, plug in our value, there we go. So our height is 2.264 feet, which matches the value we got on our problem, which matches the correct answer, technically speaking. So the correct answer is 2.26, and we got 2.26 feet above the target is where the cannon should be pointed, right here. That's our height, and we found our height right here. So thanks for watching. Hopefully this was detailed enough, very much comprehensive review of problem number 5, Canon. And yeah, I'll probably do more of these. I'm pretty bored, and yeah, I probably yapped way too much, but it doesn't really matter. So yeah, whatever.